Let's continue looking at gas laws and how we calculate pressures for mixtures of gases. There's a gas law called Dalton's law of partial pressure. Okay, Dalton's law of partial pressure. Dalton is the same chemist who developed the atomic theory of matter. So he's got a couple of big claim to fames in the chemistry world. Okay, the Dalton's law of partial pressure, it will often be represented in textbooks in this form. It says the total pressure of a gas mixture is equal to the partial pressures of each gas in that mixture. So here in the diagram, you see gas A. It might be oxygen, it might be nitrogen or helium, just some sort of gas, is at a pressure of 10 units. Okay, let's say that's 10 atmospheres. And gas B, we'll say that's argon or maybe krypton gas or just some other gas, and it has a pressure of 5 atmospheres. Now if we take these two flasks, and notice they're of equal volume, and we combine the two gases, so let's just take the cap off of A here, and pour it into flask B, and then reseal it. Okay, what Dalton's law says is that the pressure of A and the pressure of B, if you add those together, that will be the new pressure for this mixture of gas. So you see the partial pressure of A is 10 atmospheres. The partial pressure of B is 5 atmospheres. So when we mix them together in the same volume container, we get a total pressure of 15 atmospheres. Okay? Now, where do these partial pressures come from? How can we determine a partial pressure of a gas if at first we just have the total pressure? Okay? So now notice something here. Okay, in our figure, inside of this flask there are 10 individual atoms floating around. Let's say that represents 10 moles. Okay, for the sake of argument, let's say those 10 atoms is equal to 10 moles. And here in flask B we have 5 atoms, so let's just make believe that that's the equivalent of 5 moles. So now when we put them together, we have a total of 15 atmospheres. We have 15 little atoms here, or 15 moles. So a partial pressure from a total pressure can be calculated using something called the mole fraction. Okay, what we call a mole fraction. All a mole fraction is in our case, let's say for A here, there were 10 moles, and the total number of moles were 15 moles. So the mole fraction then is 10 over 15, or 2/3. Okay, 2/3. Now there are no units on a mole fraction. If we were calculating the mole fraction for B, gas B here, we would have 5 moles out of a total of 15 moles. So 1/3 is the mole fraction. Okay, what that represents is 1/3 of all the moles in the gas mixture is made of gas B, and 2/3 of all the moles in the mixture is made of gas A. Okay? So let's say, for example, let's do a new example here. We have a mixture of gases here in a box. Okay, so we've got gas molecules floating around in here. Okay, and we realize that we take measurements and we are told that the total pressure is 5.5 atmospheres. Okay, that's the total pressure. And the partial pressure of A in there let's say, is 4.0 atmospheres. Okay. Well, if we know that the partial pressure of A is 4.0 atmospheres and the total is 5.5, then our second gas that's in our mixture has a partial pressure of 1.5 atmospheres. Now, we can use these values to help us figure out the ratio of the two different gases in here in terms of moles. And from moles, we could go to molecules using Avogadro's number. So if we take the total pressure and we multiply it by the mole fraction of A, that's going to equal the partial pressure of A. And if we take the total pressure, 5.5, multiply it by the mole fraction of B, we will get the partial pressure of gas B. So I hope what you're realizing as you watch this video is that partial pressure of a gas is dependent upon how much of that gas, how many moles, how many molecules are present there. Well, let's put in our numbers here. 5.5 atmospheres, mole fraction of A, and the partial pressure of A is 4.0. Okay. So we can solve then for mole fraction. 4.0 over 5.5. Okay. And this, if we wanted to reduce this further fraction form, it would be 8 over 11, or if you wish to put it in decimal form, let's see, 8 over 11 is about 0.75. Let's get the exact here. 8 divided by 11. It's 0.73 is the mole fraction of A. And the mole fraction of B, we have 1.5. Mole fraction of B, total pressure is 5.5. So mole fraction of B is 1.5 over 5.5, which is 3/11 if we wish to have it in fractional form, or if we want to have it in decimal form, it would be 0.27. Okay. So we can realize that the two gases we have here, A and B, that it looks like they're in about a ratio, it's somewhere around 2.5 to 1. Okay, so if we go 0.73 to 0.27, we find that that's a ratio of about 2.7 to 1. What that helps us realize is in our gas mixture, we have 2.7 moles of gas A for every mole of gas B. Or if we thought of it as just individual molecules or atoms of gas, we have almost 3 atoms or molecules of gas A for every molecule or atom of gas B. Okay, this is a way with our atmospheric air that's surrounding us each day. It's a mixture of lots of gases, such as nitrogen and oxygen, carbon dioxide. Okay, we've got all these different gases floating around us. They keep their individual properties, but each one has a partial pressure based on the presence, the amount of moles there in that mixture. We only process the oxygen. We need that to sustain our lives. But each one of those gases, the nitrogen, the carbon dioxide, what noble gases are there, they each exhibit a partial pressure, and the sum of those partial pressures gives us our total atmospheric pressure that we see on the television weathercasts or online at the Weather Channel's website or so forth. Okay? So Dalton's law of partial pressure states that the sum of the partial pressures equals the total pressure of a mixture of gases, and that partial pressure exhibited by each gas is the product of the total pressure and the mole fraction.